until the verbs get serviced and then it starts executing again. So that's why you want to have as many verbs as possible, because you increase the chance of that device being busy. So I'm not going to get into details, but let me say here one thing. First of all, it's easy to gauge the use of resources. There is a so-called CUDA calculator, and if you Google CUDA calculator, it will open up an Excel spreadsheet. And there, the only thing that you have to enter is the number of threads that you have per block, the number of registers that each thread in the block uses, and the number of the amount of shared memory that a block uses. So these pieces of the 3 pieces of information, and it tells you immediately at what percentage you run out of the potential of that piece of hardware. And you want, the rule of thumb is, in an ideal world, you're at 100%. 100%, it means that you use very little shared memory per block, and it means that you use your threads are very careful in handling registers. They don't burn too many registers. And what does that translate into? If you have little shared memory, it means that you stand a chance of putting many blocks on one SM. Okay? And that it can be done because you ask for a little shared memory and you ask for a small number of registers. Okay? It boils down to that. And you have to think a little bit about it, but it's not rocket science, really. And if you want to play with like various scenarios, like what happens if I reduce the number of registers per thread? Then you just type in and it tells you now you are at 66% utilization of the hardware. And this is what you want to be. You want to be 66 or above. And you're on the safe side. So I'm not going to talk about this anymore. It's basically, just an explanation of what I told you. And this is the calculator. And see, this is the 3 pieces of information that you enter. I told you the number of threads per block. Here, then you say, I have 256. The number of registers per thread, and this guy used 8. And here, the amount of shared memory in bytes that each block uses, and it was 2,048 bytes. And based on that, everything else is computing, and it shows you plots, and it tells you, you are here, you're at 100% occupancy, which is good. Now, how do you know the number of registers used by a thread? There's a compile flag. It's called -keep. If you compile and you add this flag, -keep, it will save that's what is called the CUBIN file, CUDA binary file. CUBIN file. You open it and it's kind of like a bunch of, a lot of garbage in there. But the first thing that you can read, actually it says that it tells you the amount of, I don't know if I have a slide here. It tells you the amount of, right here. So you compile with the -keep flag, and you see some binary code like this that, to me at least, doesn't make any sense. But in the beginning, it tells you this is the name of the kernel. It says math vector multiplication kernel. So this is actually the name that I had in the kernel. And it says shared memory used 168 bytes, registers used 8. So with this information, you can go to the CUDA calculator, CUDA occupancy calculator, and right there you know how you're going to fare. So it's kind of like straightforward. If you want to debug, there are 2 ways you can go about it. One is called debug emulation mode. And what happens is it generates code that runs on the host, but it mimics the same, thread block structure. However, there are some. I listed here three pitfalls. You can. This is not quite like GPU executing on the GPU, because the pointers can be messed up. The synchronization can be different, so it's not quite the same thing. However, next week NVIDIA is going to release. They call it Nexus. Nexus is an integrated development environment for CUDA programming. And in Nexus, actually, you can debug code running on the GPU. I haven't done that. I saw it on YouTube. And it looks very, very impressive. I mean, you can actually, it takes you down into the GPU. So actually you can see, you can access the shared memory, you can have the registers there. I think that is going to be a significant step forward. Unfortunately, it's only for Windows. So
yeah, sorry. For Linux, there is debugger.
Right. For Linux, there is I think it's. I don't know what the name of it is.
It's like
GDB or something. It's GDB-like, but I don't think that it's as neat as this Nexus thing that is going to be released next week. Okay, so what applications stand to benefit in engineering of this? So finite element analysis, Professor Suresh does some bone, Josh, you know that, right? Bone modeling or something like that?
Yeah, it was one of the things we worked on.
Right, so, Monte Carlo analysis, molecular dynamics. There's a group at University of Illinois at Urbana-Champaign. They got, impressive speed-ups here. Granular dynamics, this is something that we're working on. Image processing, it's huge there. Agent-based modeling, also very, very useful. So in general, if you have a piece of code that uses this single instruction multiple data paradigm, remember that example that I gave you with 25,600 pictures that you want to paint? If that's the model, you have to work on many data with the same instruction, single instruction multiple data, then the GPU computing is something that you want to use. Okay, some examples of speedups. Remember, when we look at the CPU and the GPU, the speedup was 12, right, in terms of like flop rate. And now look at these numbers here, like 149. We end up in collision detection 180 times faster than the sequential one, and it's precisely because those SMs they never starve. They're never data starved. So that's why you see some really nice speedups. So I think in high performance computing, there is this shift from sequential to parallel computing, and at the beginning of the presentation I told you about, it's not like we want to, but the chip industry is moving in that direction. The support for parallel computing, unfortunately, is very it's not homogeneous. That's what it was meant to say. Yeah, so inhomogeneous. GPU is not alone in this race to capitalize on parallel computing for scientific applications. You have cloud computing and many core architectures and so. But in the end, on the software side, the players, as far as engineering computing is concerned, I'm not talking about like in finance, there's a different story. But here, how can you leverage a parallel hardware? You can have threads like pthreads, and you have also Windows threads, OpenMP, MPI, the TBB library, now OpenCL. This is in addition to CUDA that we discussed about here. On the hardware side, you have the GPU, and you have NVIDIA and AMD. Well, you have the fusion idea, and the AMD here is doing a very good job. So basically, the question is, why have GPU and the CPU on different chips? AMD put them on the same chip, which will eliminate that umbilical cord, which is the PCI Express connection. You have cell blades, you have cluster computing, like the IBM Blue Gene at Argonne National Lab, at Livermore National Lab, and you have cloud computing like Condor. I listed here some sources of information. I'm not going to go through them. This is going to be online. And conclusions: shift to parallel computing. Hardware changes at a faster pace. Software is playing catch up here. CUDA is a bright spot. in the software landscape that otherwise is pretty bleak. GPU computing is not the silver bullet. There are many applications that are not suitable for GPU computing. And